All right, so this is the lab review session. So there are 6 people here with us, and then if you're viewing this at home, then that's fine too. So last class we left off talking about the 5th lab we did this semester, which, by the way, you can find this list on the Science Learning Center website. It's toward the end of the Chem 131 segment, and it says Lab Practical Review. So you already have access to this list. Number 5 is the 8 bottles reaction. When we were together yesterday, we talked about what we could ask you in that lab. So let's move forward. We're going to talk about the 6th lab, which was the molar volumes. On this list here, it says the things that you should know are what are oidiometers and how do they measure gas, and then also equilibrating the gas pressure in the oidiometer with the air pressure. Now remember, when we were doing this lab, we had ultimately what we were trying to find is what is the value of R. And remember, R, if we take our PV equals nRT equation, would be PV over NT. And so the important part of this lab was for you guys to use whatever equipment you had to get measurements for these 4 parameters. Remember what you did is you took your oidiometer. In the bottom of your oidiometer, you put a little plug with a string that was tied around some magnesium coil. In that oidiometer, which was completely filled all the way with liquid, you put in some hydrochloric acid. Ultimately, the hydrochloric acid came down here. It reacted with that magnesium coil and it made H2 gas. So you should be able to tell me what types of, if I gave you a different metal, let's say instead of magnesium to react with HCl, you should be able to do that reaction. So for this one, remember it was magnesium plus HCl goes on to do a single displacement reaction. In this case, it made magnesium chloride aqueous, who cares, plus H2 gas. This is what we were collecting, and at this point, which we should balance it. So there, now we're balanced. All right, so that was the reaction that you guys did in lab. And ultimately, you were collecting gas that was coming up here. Now, the pressure parameter, does anyone remember where you got the pressure parameter? The barometer that was on the wall. Now, yeah, that was the pressure of the room. That is a very important concept because after the reaction was done, and let's say that this magnesium was all gone, your water level, let's say, was there, okay? So now you had your water level here. All your gas that you collected was there. The pressure that you read from the wall was the pressure of the room. Now, after you did this part, you put this whole apparatus into a big graduated cylinder. And what was important about the level of the water in the graduated cylinder? It should be the same. So in this case, the level of the water in the graduated cylinder, we would have to move the oidiometer up and down. We'd have to move that up and down until the water levels matched. Why did we have to do that? That's right, because we read the pressure on the barometer, and the pressure on the barometer was based upon the room pressure. Well, that's lovely, but the only way that we would know what the pressure of the gas was is if we could compare it to something. We know the value of the room pressure. If we move the oidiometer up and down to where the levels match, then the pressure of the gas inside is equal to that of the room. Let's say that this weren't the case. Let's say that instead of having them equal, let's say we were to have the pressure the water level in the graduated cylinder, the large graduated cylinder, to be up here, right? Instead, have the water level in the graduated cylinder up here, and then the water level in the oidiometer itself down here. Would this indicate that the room pressure is higher or lower than the pressure of the gas inside here? Which pressure is greater, the room pressure or the oidiometer pressure in this case? The oidiometer, that's right, because the oidiometer is pressing down harder, so therefore in this case the oidiometer pressure is higher. And consequently, if we were to instead have the water level here in the graduated cylinder too low, then that would indicate that the room pressure was higher than the pressure of the gas inside. So remember, we match those levels up in order to say that the pressure that we read from the barometer, aka the room pressure, is the same pressure as the gas that's in here, because remember, we need to get these parameters. Now, I did that, I measured the pressure. Now that the water level is equal, I have a question for you. The water level is equal in the graduated cylinder and in the oidiometer, all right? So now my question is the pressure now of the hydrogen gas inside this oidiometer the same as the room pressure? Is the pressure of the hydrogen gas inside the oidiometer the same as the room pressure if the water levels are equal? Everyone says no. Good answer. Why is that? Right. Remember we said Dalton's law of partial pressures says that the pressure inside here is actually equal, the pressure inside the oidiometer is actually equal to all of the different gases that are in that oidiometer. Well, since the hydrogen gas bubbled through water, we now have water up here. And actually, if you think back to our class yesterday, we talked about vapor pressure. So really what you guys were subtracting out was the vapor pressure of water. Remember, vapor pressure of water will change with different what? Vapor pressure is temperature dependent. So in this case, you guys read the temperature of the room, which is good because we needed it anyway. Okay. So you read the temperature of the room, and then after you did that, you took the pressure that you gathered from the room, made sure that the levels were equal, then subtracted out the vapor pressure of water at that temperature. Now, volume. How did you get the volume of the hydrogen gas? Remember, there are actually little tick marks on the oidiometer.
Oh, so we kind of measured like
Yeah.
after, because didn't it go down like once you put it in, or up? We did measure like.
That's right. So you needed to measure the volume based upon the tick marks when the water levels are equal. Okay, that would tell you the volume at the correct pressure. All right, now. Just be mindful, these tick marks might not go from 1 to 100 this way. They actually are reversed. They start up here, 1, 2, 3, 4, and all the way down because you're measuring gas, and the gas is going to be up at the top of the oidiometer. So that makes sense there. All right, next. So we have now the volume when the water levels are equal. So then that way we know that the pressure and the volume are correct. Temperature we already measured. We're going to change that to units of Kelvin. N is the moles of hydrogen gas. How did we get that? Do you remember? Anyone want to take just quickly describe what they did in this experiment? You took some magnesium metal, rolled it into a ball, you put it in the bottom of the oidiometer, you put hydrochloric acid in here, turn this upside down, the hydrochloric acid reacted with the magnesium, and it made H2 gas. Now, how did we get the moles of the H2 gas? Yes, ma'am?
I know that R is a constant, so we just use the equation and plug everything.
Well, ultimately, for this experiment, we were trying to find R. Do you remember that was one of our goals, was to find
okay.
R? So, yeah, go ahead, Zara.
Can we find the moles of magnesium?
That's right. So we have the mass of magnesium that we put for our coil. So we have the mass of the magnesium, then we use the balanced chemical equation to go from mass of magnesium to moles of magnesium to moles of H2. So that's ultimately what we did. All right, so we did the PV equals nRT equation. That's ultimately what we were trying to find out. What's the value of R? And then also, the purpose of this is we wanted to find the molar volume of a gas. In other words, what is the volume of 1 mole of gas at STP is what we were looking for, okay? So now we have all of these parameters which we just measured, and we use the combined gas law. So we have our P1, V1 over N1, T1. And we used our combined gas law to go to P2, V2, ultimately is what we were trying to find, over N2, T2. Okay? What value should we put in for P2?
Oh, the pressure after we put it in the water.
Nope, that was this. Standard, what is that then? 1 ATM. So 1 ATM here, volume is what we're trying to find. N2 is what? What value did we put here? 1 mole, because it's the molar volume of a gas. And then T2, this is at STP, so what would that value be? 273.15. Remember, for the gas laws, it's 273.15. For the enthalpy equations, it's 298.15. So just don't get confused there. It's the 273. 0 Celsius is ultimately what we're doing here. Okay? So that's the second thing. We're solving for V2. Dalton's law of partial pressure, we already talked about. We needed to subtract out the partial pressure of water at that temperature because we had H2 and water, which was giving us the P total, which has already been calculated. Does anyone have any question about the molar volume of the gas equations or anything like that? Okay. Any other things you want to talk about with regard to this experiment? Let's quickly, I'm going to look at I printed these out. I'm going to look at the pre-lab questions just to make sure I covered all the bases here. And the post-lab questions, just so I can see what's going on.
Is this sheet on Blackboard?
It's on the Science Learning Center website.
Okay.
Let's see. Pre-lab questions. They asked you to write a balanced chemical equation for the reaction that you were doing. Classify this reaction as combination, decomposition, single replacement, or double displacement. So we said single replacement here. And then they gave you a bunch of values and basically that they got during the experiment, and you had to solve and determine the percent error. Percent error, let's talk about that then, since this is what's being asked. Percent error is equal to the absolute value of what you actually got, salute, minus what you should have gotten. So remember, and then by the way, over what you should have gotten times 100. I put up here actual, meaning what you actually got, right? Sometimes you might see this listed as experimental. So what did you get during your actual experiment? Theoretical is what the accepted value is. So remember, for this lab, you wanted to find out what is the molar volume of a gas. So so afterwards we asked you, well, we know that the molar volume of a gas, according to the literature, is 22.414 liters, okay? So now, based upon your value that you got here, you needed to put what you got minus the 22.414, take the absolute value of it, and then divide by 22.414. In some cases, you guys might see where they don't have the absolute value, in which case that would tell you were you higher or lower than the accepted value. Okay, so if it's a positive value, it means that you were higher. If it's a negative value, it means that you were lower. You can just use the absolute value equation, no problem. Okay? Anything else here for molar volume of a gas?
Wait, molar volume of the gas or molar mass of CO2?
We didn't do molar mass of CO2 lab. Although it's a fun one. All right, so molar mass of CO2, we didn't do any, we didn't even do that lab, so that you will not see on your lab practical. Okay. Calorimetry, let's move on and talk about that one. This was the Hess's law equation lab, right? So, first thing it says is to remember that delta T means final minus initial. You guys already got that, no problem. Endothermic means that the reaction absorbs heat from the surroundings and the surroundings get cooler. And if that is the case, then delta T should be negative. Exothermic reactions give off heat and the surroundings get hotter, the delta T is positive. The thing that trips people up about this one is if you are doing an aqueous reaction, okay? So normally, okay, let's think about when you're not doing an aqueous reaction. Remember you take those hot hand warmers out of their package and then you shake them around a little bit and they start to get warm. What is happening there?
It's reacting.
Whatever it is that's inside of that pouch is reacting with what?
The air.
Right, and particularly oxygen in there. So you're oxidizing whatever it is that's in the hot hands. That reaction is exothermic, so the heat is released and go into your hands, right? So in other words, the reaction gives off heat and the surroundings get hotter. What happens if we have a reaction that is aqueous? For example, we have a cation here in one beaker, we'll say. In this beaker, we have an anion. We take them and we mix them together into a larger beaker, and we make some ionic compound. I understand that I'm doing this very simply, right? I'm only saying that we have one cation, one anion. That's not going to be the case. We're going to have several cations, several anions. We'd also have counter cations and anions in these. When they come together, let's assume that the temperature of the water to start, initially is equal to, let's say, 25 Celsius. And then the temperature of the water at its lowest point was 22 Celsius, okay? So in other words, we started at the water that is containing these ions was hotter to start than it was after all was said and done. Hotter to start than what it was after all was said and done. Is this reaction, mixing the cation and the anion, is this reaction endothermic or exothermic? The answer is that this reaction is endothermic. The reason being is because the heat is coming from the water and going into this system in order to make that ionic compound. Okay, so it's an endothermic reaction because the system itself, which remember are these ions, the system itself is what's gaining that heat. Where is it getting it from? It's getting it from the water. Some people will say that, the water is not a surrounding, it's part of the system. That is not true. The water is not participating in the chemical reaction that's taking place. So some people think that since the water is getting cooler, that means that it is releasing heat to the surroundings which are out here. That's not true, right? The water is actually part of the surroundings. Just be mindful of that. Okay, the next thing to consider is, so let's say that this were, so we said that this were endothermic, right? So that means that the delta H is positive. All right? If we wanted to do an experiment in order to calculate delta H, we could say that delta H is defined as what divided by what? When we say here that delta H is positive, aka it's endothermic, right? It's endothermic. Since this is endothermic, what does that mean?
It means that the sign is positive.
And what does that mean with regard to what's going on? Is gaining heat. Thank you. What is the variable that we use for heat? Q. It's not delta H. So what is delta H then? Delta H is equal to Q over Q over the number of moles.
Oh, delta T?
Q over the number of moles.
So the temperature does not move that at all.
Right. Nope, this is just talking about delta H itself. What's happening to the heat? and how many moles of stuff is giving me that much heat, okay? Ultimately, delta H, remember if we look up delta H in the back of our textbook, delta H is given in kilojoules per mole. In other words, how much heat is exchanged for 1 mole of reactant. So if I were to have 1 mole of ions, 1 mole of positive ions, 1 mole of negative ions, and did this reaction, then whatever value I got, Q, would be the same as delta H, okay? Is it possible for, if, let's say that this reaction was, so this is endothermic, is it possible for delta H and Q to have different signs?
Yes.
No.
In what case?
Well,
Just to show the direction.
Well, we're showing the direction of how the heat is flowing. That is true. But is it possible to for them to have different signs? For example, positive here and negative here.
no, because you can't have negative moles.
That's right. So if this were positive, which we are saying it is in this case, then this could not be negative because there's no such thing as negative moles. Okay, so delta H and Q always have the same sign, always. Okay. What else is on here? Heat and enthalpy equation. So remember our Q solution equals mc delta T, and our calorimeter equation is that the Q of the cal is equal to C cal and delta T cal. I had a couple questions about this during the lab. You'll think back, you'll say, okay, well, it says what's the temperature of the solution, what was the highest temperature of the solution, and then right below that it said what was the temperature of the calorimeter. Do you remember that? And what did you do with those values? What was the temperatures of both of those? They were the same thing, because however much heat was released by the system, right, ultimately part of it got absorbed by the calorimeter, in which case both of them would have been the same temperature. Now, the total heat that was released by the reaction, you have to consider how much did the calorimeter absorb, plus how much is still in the solution. So the Q solution plus the Q of the calorimeter would have been whatever your total Q would have been, right? How much heat is released into the liquid itself? What's the Q of the calorimeter? That's based upon the C cal and the delta T cal. Where did we get the C cal value from?
Isn't it a constant?
It is a constant, and it's called the calorimeter constant, but where did we get that from? How did we? Yeah, we gave it to you. How do you think we got that value? Through a separate experiment. So basically a separate experiment was conducted in order to calculate this. Once it was calculated, we said, okay, now that we know what's the heat capacity of the calorimeter itself, we know every time we run one of these calorimetry experiments, always C cal will be the same, okay? I will tell you that this is a little bit trickier of a concept for people to understand exactly what was happening with that, and which means that probably we don't emphasize this. Okay, it might be on there, but it probably isn't emphasized. I wouldn't spend too much time on that. Calculating Q and delta H, we already talked about that. Delta H is Q over number of moles. We talked about how to calculate Q. Q would be the Q of the solution plus the Q of the calorimeter. That would be the Q of the reaction. Q of the solution plus the Q of the calorimeter equals the Q of the reaction. Make sure that your signs are consistent here, right? And then the delta H for reactions means the amount of heat that is exchanged during that reaction, right? This is, in other words, the thermochemical equation, where we can use that value from the delta H value in order to calculate something else. Does everybody know what I'm talking about or no? I can give you an example. Let's say that this reaction, I'm going to make up some numbers here. Let's say that this reaction has an enthalpy value of 100. We'll make it easy on myself. Let's say that we had 4 moles of H2, and I wanted to know how much heat would be released from that 4 moles of H2. Well, I could say 4 moles of H2 times 2 moles of H2 releases 100 kilojoules. Okay, so this is based upon the balanced thermochemical equation. Okay, this value is based upon the balanced thermochemical equation, and then we would have 200 kilojoules. So you say, Kyle, how much heat would be exchanged? 200 kilojoules based upon the value of the thermochemical equation and the coefficient of the balanced chemical equation. Sound good? Okay, I think that that's pretty much it for calorimetry. I'm trying to think in my head what I've seen on past practicals. And if there's something that I can think of to talk about, I will talk about it.
Is the format of the exam like all of our other exams just on paper? There's
Pretty much.
actually having to do like any sort of.
There's like, I think it's 25 to 30 questions. There's up to 10 different stations that you actually have to go to and do something. And then the rest of the questions, let's say 15 to 20, are working out on paper. Like, for example, we'll give you some values and ask you to calculate delta H.
But is it like, oh, there's 10 multiple choice and a couple short answers?
Nope, it's all short
multiple
answer.
choice. All short answer.
Mm-hmm. It really isn't bad. If you guys just do, even coming to this review, you'll get most of the questions correct. It really isn't that bad. Density virtual lab, the density one. Let's talk about what we did here. What was the overall purpose of this lab? And by the way, this was one of the pre-lab quiz questions that I gave you. What was the purpose of this lab? To find the density of the two unknowns using the equation that was gathered from starts with a C. Nope, not concentration. It's alliterative. It's 2 words, and it's alliterative. Does everyone know what that means?
Yes.
So that means that both of those words start with a C.
So it's something constant.
Nope. Good guess, though. That is a C word that we've used a lot. Calibration curve. Okay, remember? Zara told us that the goal of this was to find out what is the concentration of 2 unknown alcohol solutions. The way that we got that is, remember, I gave you 3 different alcohol solutions, asked you to calculate their density. So now you have a graph to where you have density and you have concentration. All right, if the concentration of alcohol, let's say, is 0, well, the density is 1 because it's pure water. If the concentration of alcohol is 100%, well, then it would be down here, and pure alcohol is 0.789 grams per milliliter. You don't need to know this number. This is just me reminding you of what we did. So then after that, you guys put in a couple other dots here, right, based upon concentrations that were given to you. And then you plug that value into Excel. What did Excel do? They gave you a y equals mx plus b equation for this line. And then what did you do? You calculated the density of the 2 unknowns. Once you got the density of the unknown, what did you plug that density in for, y or x? Let's take a look at how I've graphed this here. Y. In this case, it was y because I put density on the y-axis. Be mindful of that, okay? Be mindful of which value, y or x, you're plugging that in for, okay? Because we've been known in the past to use calibration curve information that is not based upon density at all. It's based upon something totally different. And you need to look at your parameters, your y value, your x value, and figure out, what do I need to plug this value in for? Do I need to plug it in for x? Do I need to plug it in for y? Okay? So let's talk about this. Different ways of expressing concentrations. Molarity is one. It's basically some amount per some unit volume. Okay? Some amount per some unit volume. Density versus molarity versus weight percent versus percent by volume. We talked about density. Molarity is moles per liter, moles of solute per liter of solution. Weight percent is the mass of solute over mass of solution times 100. And percent by volume is volume of solute divided by volume of solution times 100. The worst of these is the percent by volume. And the reason being is because volumes are not additive. Remember, we talked about that. If you have 10 milliliters of ethanol and 10 milliliters of water and you mix those two things together, how many milliliters of solution do you now have? Who knows? It may be 20, it may be less than 20, it may be more than 20, who knows? It depends on how those molecules interact with each other. We're kind of talking about that right now in chapter 11. Volumes are not additive, okay? So the worst concentration unit is percent by volume. Yes, ma'am?
Would you say that equation was percent by volume?
Volume of solute out of volume of solution times 100. And the important thing about that is just making sure that those units are the same. Milliliters over milliliters, liters over liters, whatever it is, okay? Gallons over gallons, who cares? It will all give you the same as long as if they're the same units. Plotting and calculating straight lines, y equals mx plus b. I don't know what else I can talk about other than using this. If they gave you a table of x values and y values, 1, 2, 3, 4, 2, 4, 6, 8, could you, from this information, make a y equals mx plus b, line? Could you give me an equation of a line from this information? Remember, this is the change in y over the change in x. That will give us the value of m. And then b, we just plug whatever the value of m is, we take one of these and plug it back in and solve for b. Do you remember doing this in algebra? If not, I can do it for you. Change in y over change in x. So y goes from 4 to 2. X goes from 2 to 1. And 4 minus 2 is 2. 2 minus 1 is 1. So the value of m is equal to 1. Or I'm sorry, is equal to 2. Okay? So now we say y equals 2x plus b. We need to solve for b. All right? So we take any set we want. Let's take this set. We plug 2 in for y. We plug 1 in for x. And then we solve for whatever b is. So 2 times, in this case 1, plus b, we don't know what that value is yet, is equal to, according to this, 2. So in this case, let's solve for b. 2 times 1 is 2, minus 2 from both sides. 2 minus 2 is equal to b, which is equal to 0. b in this case is 0. Y equals 2x plus 0, or simply y equals 2x. Okay? This you may have to do, you may not have to do. Okay? But this is basically what your Excel was doing for you in this lab. Was calculating the y equals mx plus b equation doing this math. Because it says calculating straight lines here, we went through an example of that. Solving simultaneous equations. I'm trying to think about what this means. I'm not sure what that means.
Substitution.
Oh, like substituting into the y, probably. Substituting a value in for the y equals mx plus b equation that was provided, probably.
Is that like the ones that we used to do in algebra where it was like they'd give you like 2x plus 3y equals 6, and then they'd give you like x plus y equals
And then you solve
10,
for the,
and then you solve.
no, that is, maybe. I don't think
That's
that
not-
is the case. but maybe. Yeah, I don't remember that ever being one of what we discussed. I mean,
how would that?
yeah.
Yeah.
Yeah, how would that apply here? I mean, it could if we had two different y equations for different lines, but no, that we wouldn't do that because it's not related 100% to the lab. This, you say, okay, Kyle, well, we didn't have to do this. Well, yeah, you did. You had to do it in Excel. So knowing this, how it worked, is kind of important. I do not know if this will be on there or not. I have no idea. I haven't even seen it on purpose. I haven't looked at it because I don't want to be biased in this session. All right, dilutions, M1V1 equals M2V2. The important thing to remember here is that the species must be the same. Otherwise, it's not a dilution. If it is not the same, what do you need in order to solve? A balanced chemical equation. Okay? If it's a dilution, it means that the species is the same, and you can use M1V1 equals M2V2. If it is not the same, it means it's not a dilution, and therefore you need a balanced chemical equation. You guys have done many of those examples in the past. Okay? Next, let's talk about elements. All right, this lab, we made some rules, okay? We did some experiments, we saw what happened, and we made some rules based upon those experiments. So basically, we need to be able to summarize those rules. First, halide identification and reactions with halogens. The extraction into cyclohexane, the colors of the halogens in cyclohexane, and the relative reactivities of halogens. Okay, so let's say that you mix together some potassium iodide and you mixed it with bromine water. Remember, there were two little things that you had to mix together. You had to mix together a solution that contained potassium something, whether it be bromine, chlorine, or iodine. You had to mix together potassium iodide, potassium chloride, potassium bromide, with some halogen in its diatomic state that was dissolved in water. Basically, we just bubbled some of the halogen through the water. And you had to mix these two together. After that happened, we put some cyclohexane on top and we mixed it together. Why did we put some cyclohexane on top? Because if a reaction happened here, this would be the reaction. Is everybody with me on that? Now, what goes into, so remember, cyclohexane was less dense than the water, so this is the cyclohexane layer here. And down here was the water layer. Okay, we're basing whether a reaction happened dependent upon the color of the cyclohexane. If a reaction did not happen, what color would that cyclohexane be? Not clear. Orange. Burnt orange. Why? What is turning it burnt orange? Yes. So whatever the diatomic species is what will always end up in the cyclohexane. Now you have to remember that bromine makes a burnt orange color. Iodine, I2, makes what color? Purple. And let's say that we were in a different experiment using Cl2, what color would it be there? Yellow. Okay. So, let's say that you do the reaction, you mix together potassium iodide, by the way, we can balance it. You mix together potassium iodide, aka this aqueous solution of potassium iodide, with some water that contains some Br2 in it. After you mix those two together and you add in the cyclohexane, let's say up here the color is orange. Did a reaction occur? No. Let's say that up top this was purple. Did a reaction occur? Yes. Okay. So we need to figure out first if a reaction occurred, and then secondly, what was the reaction that occurred? according to the elements lab, you would consider if we had this reaction that took place, if this reaction actually took place and this was purple, then that would mean that bromine is stronger than iodine, okay? If this reaction occurred, then that would mean that bromine is stronger than iodine. That's what that means. If up here is purple, bromine is stronger than iodine. Is everybody with me on this? Okay. If up here is orange, what would you say? Iodine is stronger than bromine because no reaction occurred. Okay. Now, what we need to remember is what trend did we actually see in this experiment? Remember, the whole goal of this experiment was to make some general blanket statements on reactivity. What was more reactive? The top of the column, for example, chlorine, or the bottom of the halogens, for example, iodine? Was iodine more reactive, or was chlorine more reactive? Chlorine. It was opposite the trend that we saw from the from the alkali metals. Okay, it was the opposite. So as far as reactivity goes, we would say that chlorine is more reactive than Br2, which is more reactive than I2. And then if we were to continue on with this trend, we would say that that also means that fluorine is probably more reactive than chlorine. Fluorine's very dangerous, so that's why we didn't do anything with fluorine. All right? All right, so if I gave you a or basically if I said up here I have yellow, and I want to know, actually no, let's not do that. Let's say up here I have orange. Which of these reactions may have taken place? So Ki plus Cl2. KCl plus Br2. KBr plus I2. Or none of the above. Which one of these may have taken place? So I should give you a little bit more information. A reaction has taken place. Let's make that statement. A reaction has taken place. Which one of these would have happened? The third one here. So Br2, that goes to MKI, right? That's what we did. If this reaction took place, which according to us just now it has, right? If this reaction took place, what would be stronger, iodine or bromine? Iodine would be stronger. Is that consistent with what we saw in the actual experiment? No, he said bromine was stronger than iodine. So would you expect this reaction to take place? No. So this reaction did not take place. This is not possible. Okay, why? Because iodine is not stronger than bromine. Bromine is stronger than iodine. So therefore, which of these could have taken place? Well, let's see what would have happened here. If a reaction took place here, what would that say? Is this possible? Is bromine stronger than chlorine? No. So this isn't the reaction. And what's more, it's orange. Anyway, so we know that this isn't going to take place. Okay? Any questions about this? It's none of the above, by the way. It's none of the above. How do I know it's none of the above? It can't be this one because this doesn't have bromine in it, and I know that it's orange. Okay? It can't be this one because I said a reaction has taken place. If I said a reaction didn't take place, well, this would be possible because Br2 is weaker than Cl2, so you wouldn't expect this reaction to take place anyway, right? So this actually would be possible if I didn't make that statement that a reaction certainly took place. Mm-hmm.
You said if it turned purple, then the Br2 is stronger, right?
If it turned purple,
And bromine is stronger.
then bromine is stronger, yes.
So then, in this case, if bromine, because it's orange, isn't like chlorine stronger?
Yeah, bromine still is stronger here
Why?
because of our trend that we learned from our lab. Whatever's on the left, if no reaction took place, then whatever's on the left, or actually no, Cl2 in this case is stronger than Br2, but no reaction took place. So this could have been what we are seeing here, but since I told you a reaction certainly took place, this eliminates this as a possibility. Okay? It's hard, this concept is a little tricky to wrap your head around. All right, any other questions about this?
I have a question about this. I think it was the last question on the postdoc.
For this one?
Yeah, it was like the two equations and there was like an x and multiplying the x. And I don't really understand like how.
Okay, two. Oh, okay. It says unknown halogen X2 was added to two test tubes which contained NaCl and aqueous NaI respectively. So let's have a look at this. We have X2 that was added to NaCl. So we have NaCl plus X2. And then we had NaI plus X2. According to this question, it says when cyclohexane was added to the top of each of these test tubes, an orange color developed in the top layer of the first test tube, while purple developed in the second. So here we have, down here we have purple, and up here we have orange. And it says identify X2. Well, because it's orange, we know that that's going to be Br2. And then it says write a balanced equation for each reaction that occurred. Well, in this case, if we were to consider this, then over here we'd have Cl2 plus NaBr. We can balance it, right? But the problem is here is, according to our trend, is chlorine stronger or bromine stronger? Chlorine is stronger. So this reaction would not go forward, right? It would go that way. In other words, it would just get stopped. It would just get stopped. And that's why we see orange up here. Nothing would happen. There's no reaction taking place here because chlorine is actually stronger. So that's why we see orange here. Now down here, is bromine stronger according to our trend?
Yes.
Yeah, bromine is stronger than I2. So here we actually would expect the reaction to go forward. Okay? So that's why we get purple and orange. Do you understand the question now? Okay, let's look at the next part. It says properties of metals. Reactivity with water. So when we took an alkali metal and reacted it with water, what happened? An alkali metal, aka like sodium. When we took sodium and reacted it with water, what happened? Yeah, so this was pretty reactive. This is the demonstration that I did. We saw that it caught on fire. Why? Well, it was making H2 gas, and the H2 gas is flammable, right? And it's an exothermic reaction. That's why we saw that smoke coming up. All right, so based upon this information, by the way, it's not balanced. I don't care. I'm not going to balance it. Based upon this information, then, what would we expect this solution to be? Acidic, basic, or neutral?
Oh, basic.
Basic. This is going to make a basic solution. Now, how can we test this? We should take some litmus paper. So if I were to take a blue litmus paper and put some of this solution on the blue litmus paper, what would happen? Wouldn't change, no change. If I were to take the red litmus paper and put some of this solution on the red litmus paper, what would happen? It would turn blue. Does everyone see here that in order to test whether it's acidic or basic, I have to take both strips of litmus paper. I cannot take just red and see what happens. I have to take both of them. Because if nothing happens on either of them, then it would still be neutral. All right, so that's what we're looking for. We're trying to see if it's neutral or acidic or basic. All right, so that's the reactivity with water. That was an alkali metal. Let's think of another metal that we did this with. You guys did it with magnesium metal, didn't you? So you took some magnesium metal, you put it into some water, and then you tested it immediately. After you tested it immediately, what had happened? Nothing. It was still neutral. So it said in the instructions, if you test it and it's neutral, then wait a little bit, right? Wait 15 minutes or something. I don't remember what it said. You guys came back 15 minutes later, tested it again, and it was? It should have been basic. It should have been basic. These are alkaline earth metals, which means that they don't immediately react, but they do react with the water, okay? But it just takes a long time to do it. So they should have been basic after a while. So metals, alkali metals, turn it basic. Alkaline earth metals, turn it basic as well. It just takes longer for that to happen. So based upon our discussion now, most metals that we've seen reacting with water turns it basic. All right. Let's think about. Actually, I'll get back to that in just a minute. Properties of metals, we said that it turns the water basic. The conductivity, they conduct, right? Shiny, especially when they're cut. Because the alkali metals are pretty reactive, they oxidize pretty quickly. So they lost their shine pretty quickly. Relative reactivities of alkalis and alkaline earths, we just talked about that. Properties of nonmetals. Actually, I want to go back up here because we also did some metal oxides. We took metal oxides and put them in water. Remember when I burnt the magnesium metal and it turned really bright white? Now, after that it turned really bright white, whatever was left over, that was the oxide of magnesium, so magnesium oxide. I took that magnesium oxide and I put it in water. And we came back a little bit later and we tested it. It turned out that it turned the water basic. Actually, this is the end of that equation. It turned the water basic, okay? So, and it's already balanced. This is what we expect. Metal oxides turn water basic. Metal oxides, okay? If I were to do the same thing with potassium, what would happen? Same thing. If I had a potassium oxide and reacted it with water, it'd turn that water basic. Now let's go down here and let's talk about our nonmetals. Remember we took P2O5 and reacted that with water? What happened to the water there? It turned acidic. It turned acidic. This is a nonmetal oxide. Okay, nonmetal oxides turn water acidic. Remember, because the whole purpose of this lab, remember, was to make general statements. These are general statements that I'm making. Metal oxides turn water basic. Non-metal oxides turn water acidic. CO2. CO2, is that a metal oxide, non-metal oxide, or it's not either? Non-metal oxide. Would you expect if I took CO2 gas and bubbled it through water, what would I expect to happen to that water? It would turn acidic. This is the part of the rationale for the whole global warming debate on whether or not this is happening. Well, it's saying, well, if this is happening because CO2 emissions, then basically when it rains and it rains through CO2, what's happening to that rain? It's turning into acid rain, and so that rain is ultimately ending up into the oceans or lakes or wherever it's ending, and so also ultimately those lakes are turning acidic, and that's what's killing fish, is what they're saying. Experimentally, this is what we see. Okay, whether you believe in global warming or not,
So nitrous
experimentally,
oxides
this is what we see.
Nitrous oxides would do the same thing.
That's correct. Actually, nitrous oxides, NOx, and sulfur oxide, SOx. You might have heard of these in like an environmental class or something, NOx and SOx. They do the same exact thing. Where are NOx and SOx emitted from most often, or the most common emission?
Wait a minute.
Cars is the big one. You guys ever heard of like a catalytic converter?
Yes.
It's
Oh, yeah.
catalytically taking NOx and SOx and turning them into things that don't make acid rain, ultimately, is the idea there. Okay? Let's see. Cool, we're applying chemistry to real life. How fun.
Wait, so would that mean like hybrid cars do that less?
That's the thought, considering that they are battery operated. But ultimately, this is a funny debate to me because let's say that you were to have like a completely non hydrocarbon engine, right? Let's say that you have an electric car, right? Yeah, like a Tesla, let's say. Are you adding to acid rain? Is anything that you're doing adding to acid rain?
Yeah, because making
Yeah, because you still have to plug it in. Where do you think that electricity is coming from? A bulk of the electricity that's made for your car is from burning hydrocarbons. Oops. So until really we can harness energy in a different way, or enough energy in a different way other than hydrocarbons, you can make all the Teslas you want. That's not going to do anything as have an environmental impact. People say, well, yeah, but not 100% of the energy that is made into electricity for your car is from hydrocarbons. That's correct, but a bulk of it, I would say like 90%. I don't know, this is a number I'm making up, so don't go prove me wrong. Or actually, go prove me wrong. Give me an actual number so I'll be a little more knowledgeable there. But it's something crazy. It's in the 90s, I would be almost certain of. Oh, but what about, hydroelectric electricity, like a dam? Yeah, that's lovely, but it doesn't harness enough electricity for what we are using. All right, so non-metal oxides in water, we say that they turn the water acidic. And then using litmus paper, remember, be very careful. You have to use both litmus papers to prove this to me. Do I take the litmus paper and dip it into the solution? No, I take a glass stir rod and apply it to the litmus paper, right? Because I don't want litmus. Litmus is actually a molecule. I don't want litmus in my solution. And that's pretty much it for this lab. Any questions about the elements lab? Yes?
Is there anything that can change both litmus and hydrogen?
Not an element, no. But there are molecules that are made up of elements that can either be acidic or basic, sure.
Do we react them with water because water is neutral?
Yeah, so ultimately we want to find out whether it turns the solution to acidic or basic. Stoichiometry, balancing chemical reactions, net ionic equations, and acid-base reactions. What is the biggest thing, the biggest take-home message? Because a lot of you guys, when we were doing this lab, it was very confusing for you, right? What did I recommend that you make? A what table? ICF table, remember that? Now out of I, which is the initial number of moles, C, which is the change, how much the moles changed, and final, how many moles of whatever it is ultimately are left over, which one of those were most important, I, C, or F? C. You take whatever the moles are in C all the way across and you divide them by the smallest. That will give you the coefficients to your balanced chemical equation. Does everybody remember that? Okay. And that's pretty much it. You guys know full molecular, full ionic, and net ionic equations, right? We did that also in 8 bottles. Acid-base reactions, that is just going to water. Ultimately, those 2 reactions could be also found in the 8 bottles. Titrations of acids and bases, balanced reactions. The thing to keep in mind here is how protic is your acid, right? Remember you guys used, what kind of acid did you use? Oxalic acid, maybe? Yeah, that's a common one for this experiment. Oxalic acid is H2C2O4, okay? Meaning that it's diprotic. There's 2 hydrogens, so each OH minus can come in and react with one of those hydrogens. So it's very important to have a balanced reaction here, okay? Can I use M1V1 equals M2V2 here? No, it's not a dilution, okay? Using a volumetric flask, let me ask you a question. I take 10 grams of acid, oxalic acid, I put it in a 250 milliliter volumetric flask, and then I add 250 milliliters of water. Do I have 250 milliliters of oxalic acid solution? I'll say it again. I take 10 grams of oxalic acid, the solid white powder, right, that you guys measured out. I put it into a 250 milliliter volumetric flask. I then added 250 milliliters of water into the volumetric flask. How much solution do I have? 250, more than or less than? More than, because that grams of oxalic acid took up space, right? So really the way that you make it is you take the 10 grams of oxalic acid, you add it in, and then you add water to the mark. How many significant figures are in your volumetric glassware? 4. So 250.0, 100.0, whatever the case is, okay? Your glassware on the outside of it also tells you its tolerance. It's basically how good is that last digit. So remember, because all values are all the known in one estimate. So is it 250.0? If you fill it to that mark, maybe, but it has a little bit of wiggle room there too, right? Because it's an estimated value. On the outside of your glassware, it'll tell you how much wiggle room you have. You don't need to know that for the practical. I'm just telling you. Converting molarity to weight percent. So let's say I have something that's 5 molar. I have 5 molar NaCl solution, aqueous. How do I go from 5 molar of NaCl solution aqueous to weight percent? First thing I would recommend is that we remind ourselves of what is weight percent. Weight percent is the grams of solute, in this case NaCl, divided by the grams of solution. So what I need to do is get this into this. How do I do that? The biggest, the most important part is say whatever unit this is, assume I have what? In this case, 1 liter. Because remember, molarity is moles per liter. So I assume 1 liter of solution. Always assume whatever is in the denominator of the unit will liter of solution. 1 liter of solution. Also provided in this question would have to be the density of the solution. Okay? After you get that information, you can solve, but you have to do this part. This is the secret to solving these, is to assume whatever is in the denominator. Because remember, what happens if I had 2 liters of solution? Has the concentration changed? If I had 1 liter of solution, and then now I have 2 liters of solution, is the concentration the same? Yes, it is. It's a concentration, okay? So 1 liter of 5 molar solution is the same concentration as 2 liters of 5 molar solution. Really, you can assume whatever you want. It's easiest to assume whatever's in the denominator, because then I have 5 moles of NaCl. Can you guys take 5 moles of NaCl to grams of NaCl? Sure. Can you take 1 liter of solution to grams of solution if you have the density? Sure. Okay, so that's the secret, is to assume what's in the denominator. Reading a burette, Burettes have tick marks for every 0.1. So I have, let's say I have 36 here, I have 36 here. What would I have up here? 35. Remember, Burettes read downward. Okay? So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay? So what happens if I have my line right there? That would be what? 4, well, I know my lines are all over the place, so I'm cool with whatever. 35.4 something. In this case, I'd say 4.1, 4.2, whatever you want to call it. Okay? Be mindful that because the tick marks are at every 0.1, or the tenths place, then the estimated value would be 1 after that, the hundredths place. Okay, make sure you read to the correct number of significant figures. By the way, reading to the correct number of significant figures is part of our measurements lab. However, it has been in every lab since. So do you think that it is likely that you will have to read to the correct number of significant figures in any of these experiments? Certainly. So please, that's a huge part of this practical. I'm giving away answers now, right? Not really, because you still have to know how to do it. Just make sure you're reading to the correct number of significant figures. All right, reading a burette, we just talked about that. Determining the end point. We talked about indicators last time we met in lab. Indicators tell us the end point of a titration. What does that mean? End point versus equivalence point. What does that mean? The end point is when there is a color change. So whatever pH your indicator changes colors, whenever it changes colors, you'll know that it's that pH, okay? We use phenolphthalein. We actually could look up in our books, even, it's in our books, it tells us what pH does phenolphthalein turn colors. I can't remember off the top of my head. I want to say it's a little, I think it's like 8 point something or 9 point something. I can't remember exactly what it is. But it says basically that phenolphthalein changes colors at this pH. Okay. What's that? Yeah, phenolphthalein smells really good. Okay, so that's what changes colors. Phenolphthalein at whatever pH. The end point is the pH at which the indicator changes colors. Okay? What is the equivalence point? That's right. That's when the moles of the acid are equal to the moles of the base. The moles of the acid are equal to the moles of the base. In other words, both of them having been completely consumed by reacting with one another. Now, I just told you that phenolphthalein turns colors at 8 point something or 9 point something. Where do you guys usually think of an equivalence point of taking place? pH of 7. When moles of acid equals moles of base, normally you say, okay, well then the pH will be 7, it will be neutral. That's not necessarily true. We used oxalic acid. Is oxalic acid a strong acid or a weak acid? Weak acid. How do you know it's a weak acid? It's not one of the 6 strong ones that I had you memorize. I was like, yeah, maybe there's a 7th. I don't remember. But yeah, it's not. Well, it depends on if you say that chlorate is considered to be like chloric acid versus perchloric acid. Chloric acid is also considered strong in some cases. Okay, so there is 7. I just teach you perchloric and move on like that. All right. So the equivalence point is when the moles of acid is equal to the moles of the base. The goal is to have the pH of the equivalence point to be the same as the pH of the indicator's endpoint. That is the goal. We will pick an indicator that matches that pH, okay? In biology, sometimes you guys will use different indicators because of the pH of the blood. You want to make sure that you're at the right pH for blood, okay? So you use a different indicator. I can't think off the top of my head what that is. I think it's like a bromothymol blue. It's basically, do you guys know that blood pH is above 7, right? It's a little bit basic. That's based upon buffer systems that are in your blood, like with carbonic acid, phosphoric acid, things like that are in your blood. They basically make a buffer. and make the pH a little bit higher. Okay, so that's it. Defining terms. This is the last part, I think, of this review. Defining terms, titration, right? Titration is a technique that is used in order to figure out the concentration of an unknown. Remember, what was the whole goal of the titration experiment? We took an acid that we made with very good precision. We measured out the acid on a balance. That balance gave us 4 decimal places, and I think they asked you for 3 point some grams. So altogether, you had 5 significant figures in your acid, right? Then you put it into a 250 milliliter volumetric flask. 4 significant figures there. So now you know how many moles of acid you have with good precision. 4 significant figures. And then you titrated the base in order to ultimately back out and find out what was the concentration of the base to 4 significant figures. So then now we got good precision on that base. So titration is a technique. The purpose of the technique is to figure out what is the concentration of an unknown solution, acid or base. You could do it the other way around too. You could also titrate an acid with a or a very precise base, but in this case we did it the other way around. Oidiometer, this was an instrument that we used in order to measure the volume of gas that was collected and made sure that the levels of the water was equal, so we know that we know the pressure and the volume of the gas that was collected. Non-metal, metal, metalloid, you should be able to identify those and tell me a little bit about their properties. Acid-base indicator, phenolphthalein was the one that we used, right? And it turns colors at the end point. You should be able to describe what an end point versus an equivalence point is. Meniscus, remember that is the dip that's, let's say, in the burette. Every time I ask you to read a measurement off, I always go like this. And that is actually due to intermolecular forces. We get a meniscus because of intermolecular forces. We'll talk about that a little bit more tomorrow. Enthalpy is the amount of heat that is exchanged for a reaction, for 1 mole of reactant. The amount of heat exchanged when 1 mole of reactant gets converted into product. Extraction. Extraction was basically when we put the cyclohexane on top and mixed it, we were extracting out whatever liked cyclohexane better. I'll give you an example. Right now in Colorado, there is a huge business for extraction. Huge business for extraction. Does anyone know what business this might be? You can say it. Yeah, marijuana. Extracting THC out of cannabis, right? So basically, there are several ways to do it. If you go to Colorado or Las Vegas, like I was at last week, right? You might be able to buy products. I did not, but you might be able to buy products that on the outside will say THC. If you buy like a gummy bear or whatever it is, right? And this is what people are doing. On the outside, it'll say extracted with, and it will say hydrocarbons. So it's basically hexane or cyclohexane. They might have extracted that molecule out with hexane. Or it might say extracted with carbon dioxide. So basically they did a different type of extraction where they pulled out the THC that way. So on the outside they have to tell you how they extracted it because they don't want you to have any poisons in there. For example, if they tried to extract it with methanol, methanol is poisonous to humans. And so you'd be like, okay, yeah, keep your gummy bear. I'm gonna go, down the street or whatever. I don't know. Long story short, there is a lot of regulation in this business of extraction, which is why I have a full-time job somewhere else. Okay, because we sell the instruments that which will tell them how much methanol is in your gummy bear. Okay, things of that nature. So that's extraction. When I do, extraction can be done in other places, but if I talk to you guys about that, you get bored. When I teach organic chemistry, one of the concepts that we do is extraction. We pull out caffeine from iced tea, and we calculate how much caffeine is there. Or we can pull out trimyristin out of nutmeg. Okay, so it's basically an essential oil. We pull oils out of cinnamon, nutmeg, whatever you want, okay? So those are fun experiments. Extraction is basically just pulling out a molecule that, a molecule of interest. When we get a little bit further into chapter 11, I'll talk to you about like dissolves like. Tomorrow we'll talk about like dissolves like and what that means. If I wanted to, let's say there was an oil spill in the Gulf of Mexico, and I wanted to get that oil up. If I put water on top of that oil, is the oil going to grab onto that water, or is it going to kind of run from it? It's going to run from it. Oil doesn't like water. And so therefore, you wouldn't want to extract oil with water because they don't like each other, okay? Cyclohexane was able to extract out the Br2 because they like each other, okay? Or the cyclohexane was able to extract out the I2 or whatever it is, all right? That's what the extraction is. That's the lab that extraction is describing. Decanting, remember decanting is pouring off the supernatant. Supernatant is just the liquid that's at the top. We won't ask you about supernatant because this is the first time you're ever hearing about it. That is also called the mother liquor. You'll hear both of those two terms, supernatant or mother liquor, especially when you get into organic chemistry. But the definition of decanting is pouring off the top layer of liquid in order to allow your vacuum filtration to go quicker. Okay? Tipping off in titrations. Remember when after you stirred in your base, you took the side of the Erlenmeyer and you just tapped it gently against the little nozzle that was coming down to make sure that whatever liquid was still in a drop on the tip went down into that solution. That's called tipping off. Spectator ions, ions that don't participate in a chemical reaction. Endothermic versus exothermic, we've already talked about that. Any questions about these labs? If you guys, this review is I covered a lot of what you might see there. The goal of the practical is to say, if I were to ask you to calculate the density of an unknown given this calibration curve, could you do it? Things of that nature. So that's pretty much all we're looking for. I'm going to go ahead and stop the video, but you guys can ask any questions you want.